Okay, so everybody's in the right seat then, okay? Yes. Okay. Uh, I'll be there. Um, so, so when you bring up the class page, uh, go down. I changed the seating chart a little bit, and it'll be changed more next time because people have added it. I also have some information on this ISBN. I've already told you the text for this course is Emerge with Computers, version 3.0. And this is its 13-digit ISBN. This is its 10-digit ISBN. And you can get that over at the bookstore. But there's also this, I tried to look it up on the internet before, but didn't find it. But it looks like this, like that. And the 13-digit ISBN for the hard copy one is and the 10-digit one is okay. So actually, you can do with either one of these. And the thing is that, of course, this one here doesn't have the various things such as the videos, and a lot of the pictures and audio, that's on the textbook that's online. But everything that's in text is here. How much does this thing cost? Well, um, I think it's probably best to look this up on the internet, okay? Actually, what I found looking on the internet, and I'm not going to do it again right now, is you can buy this little hard copy thing for about $50. I think it's $52. You can only buy it from Cengage right now because it's a new edition, and so nobody else has it right now. There's not any uh, old versions, okay, or used versions. And Cengage has several places on the web where they sell it. And so you can get it for about $50. Also, if you just look up this ISBN number up here, you can buy just the online version. And then they have, Cengage has a place where you can get both of them together for a little less than $100. And you need to kind of look around if you haven't bought something already. If you have bought something already and are not happy with the price you paid, you can take it back to the bookstore, I think, if you haven't ruined it somehow, and then you can buy it this other way. Now, there are versions of this from previously. Okay? So here is version 2 of this. Okay, so it's not the version we're using, but I think it'll do for this class. You just have to understand that if we talk about a particular page, here it might be a little bit different. Okay, from it here, or it might on occasion be something that's not there. But by and large, I think that if you go into these version 2s, if you need to save money, just get one of these. Okay, that's better than not having one. And there are plenty of used ones of these around. In fact, I have two of them. You want them. But I hope if you do get them, you might share them somehow with other people. Okay, so that's that. Any questions about the textbook? All right. So we go back to the course content. I think I've got everything up to date. The agenda is okay. The syllabus is okay. I think I've got the TA information correct now, and the ISBN numbers correct, and the seating charts, okay, were correct until this class started. Okay, so there's some slight difference here. Okay. I tell you what, why don't you just go sit in the back row there? There's some. What was the problem? Well, I'm glad you solved it. Okay, so last time, what was I talking about? I was talking about digital technology. Okay, let's start in the front. Alan Aldico. So, Alan, what are you a freshman, sophomore, what? Sophomore, so you've already been at 1 year of college? So you're an old hand, right? In college. So what are you majoring in? Nursing? Well, you'll get a job, I can tell you that. You become a registered nurse, you know, $1,000 or more just to sign on, right? Something like that. So that's a good occupation to follow. Were you here last time? I talked about digital technology. You heard me talk about digital technology? What did I say about digital technology? Bits and states. Okay, good. So what did I say about bits and states? What's a bit? What is a bit? I'm talking to Alan up here. I'll get around to you. You know what a bit is? Okay. James Ball. James, what is your classification? Binary numbers. Thank you, but I'm talking to James right now. Oh, my bad. uh, James, you're a digital technology, right? You're an engineer technology. So you're doing computers? Why are you taking this course? You probably already know all the stuff in this course, right? What? I see. Okay. What's a bit? It's a binary digit. Okay? It's a zero or a one, right? Um, what's the difference between a binary digit and a decimal digit? Exactly. Binaries can only be 0 and 1. Decimal digits can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? So we have 10 digits in decimal, and decimal is 10, right? And two digits in binary. Binary means, right? Okay, and so he said bits and states. So let's see here. So it's Brian, okay? Brian Bevan, okay? Bevan. Bevan. What's your major? I see. So you're here for that, okay? Um, you're a bean counter, right? We call them a bean counter. And so, what's a state? Oh, you weren't here last. Oh, okay, all right. Let me go to Natalie. What is it, Bello? Natalie, how are you? What are you majoring in? Dental hygiene. Oh, I thought you like. No, I really admire you there. Not to the laugh at me standing looking at somebody's mouth for 2 hours. I mean, it would drive me. I mean, I'd go home. I just would not feel there. I don't do that when people look at my mouth every 2 hours. So I think it's a really good job. I think really good and what's the second, Natalie? A code, exactly. It's just you just assign a value, okay, to something. Okay? So if you only have one bit, only have two states, right? I mean, if you have a code, okay, with your girlfriend, and you say, you want to go out, man, zero means no, right? And one means yes, right? And that's all. That's all you need. See, you can say to your girlfriend, it's zero, one. Right? It's just a code, okay, that you attach to that. And any two values, okay, will do, right? Well, suppose I wanted to have a code for, let's say, the four directions of a compass: north, south, east, and west. What would be a way that I could encode that, okay? Is that in hot buoy, in hot net, like a net, right? Okay. And what are you majoring in? What? Pharmacy. We have a lot of pharmacy majors. How many people here are pharmacy majors? There might be more than that. Okay. So how could I encode, say, the 4 points of the compass in binary? Sorry. Yeah, you'd have to have two bits, wouldn't you? Because you'd have to have one of them could be 00. It doesn't matter how you assign the code, right? Say north is 00, okay? East is 01, south is 10, and west is 11, right? Those are all the possibilities. Okay? 00, 01, 10, 00, 11, okay? Those are the four possibilities, and you can encode those four directions with two bits, right? Um, Suppose you wanted to have 8 points of the compass. Suppose you wanted to have northeast, okay, southeast, southwest, northwest. It would take how many bits? Three, right? And so you would just have to add an extra bit here. I mean, north can be 000, okay? East can be 001. South can be 010. West can be 011. And these others, then, you can have this. It'd be 100, 101, 110, 111. Right? So there's a general principle here, then, okay? Uh, there's a relationship between the number of bits and the number of states you have. What is the relationship between the number of bits and the number of states? Okay. So let's say Andrew Casito. Yeah. What's the relationship between the number of bits and the number of states? Well, they have what? Right. Yeah. But I'm looking for a mathematical equality. Let's say B is the number of bits you have. It's one or two or three or four or five. Okay? And S is the number of states. Okay. You think of anything, it might be a relationship. I'm looking for an equality. We'll sign in. S equal. I mean, we have one bit. How many states are there? So that can be have 2 bits, okay? Got 4 states, okay? So it's 4, and it's 3 bits, 8 states. Okay. Well, let's see. Let's try somebody else. Okay, so Eric, I don't know if you're here. You are here, right? Oh, there you are. Eric, I'm sorry. Andrew, what are you majoring in? I'm sorry. We got 2 nurses here. I hope you guys are going to take care of me if I have a heart attack during class. Right? Okay. What'd you do if I had a heart attack? Are you in nursing too? Oh, okay. Let's see. Eric Chung, okay? What are you majoring in, Eric? You're majoring in nursing? Eric, can you think of a relationship between the number of bits and the number of states? Ah, I love people that have theory. You know, I'm a professor. We just love theory. Come on with a theory. I mean, after all, so this is a university. It doesn't matter. Uh huh. Yeah. Okay. Well, let's see. Allison Francis. Allison, how are you today? So, what are you majoring in? H D F S. Human Development. HDFS. Okay. Human Development and Family Studies. Did you think of equation? Can you think of an equation? Takes B to S. You see, coming up with these equations is something that we like to do in these scientific endeavors. Times. I didn't want any more unknowns. All I wanted. So it's 2 to the B equals S. Okay. And we went over that last time. Actually, I mentioned it. Okay. Now is that really right? 2 equals S. 2 to the B equals S. Well, let's test that out. There's a B. Suppose B is 0. We don't have any bits. Right? We don't have any bits, okay? Well, what's 2 to the 0? Huh? 1 state. You don't have any bits, so the state's always the same, right? Whatever it is, you know, if it's let's go eat spaghetti, it is always let's go eat spaghetti, right? The bits is no variation. If bits is 1, 2 to the first power is what? 2. So if you got 1 bit, there's 2 states, yes or no, right? 1 or 0. You've got 2 bits, okay, that's 2 to the, what is 2 to the third power anyway. 2 times 2 times 2. Okay? 2 to the fourth power is times 2 times 2 times 2. That's 2 times to 4 times. Okay. So this is a 4. Third power is an 8. Fourth power is a 16. Fifth power is a 32. Right? I mean, this S grows pretty fast. You might notice. Okay. B, if you look at the little chart I got here, B goes pretty slow. 0, 1, 2, 3, 4, 5. S goes 1, 2. We call this exponential growth. That is, if we were to graph S here and B here, then if B is 0, S would be 1, and it looks like that. I mean, it goes up like that. And it's very steep. Exponential growth is just a, you know, really amazing phenomenon. Okay. Okay. So we need to be, powers of 2 are very important in the computing world. Anybody who's been in computing very long just knows the powers of 2 from right and left, okay? It's in their heads. They know, that 2 to the 10th is 1,024. 2 to the 11th, okay, is 2,048, okay? All these powers of 2 are just there because they've dealt with it so much, okay? But it is important. Now, how many bits would we have to have to encode the English alphabet, capital letters only? If I want to encode the English alphabet, capital letters only, 26 states I need, right? I need 26 states. I need a state for A, a state for B, a state for C, right? State for Z, right? 26, okay, exactly. So I need 5 bits, okay? 2 to 5 is 32, okay? Now, I'll have 26, and then I'll have, some more left. I'll have 6 of them left over, right? But I can let A be 0, 0, 0, 0, 1. That can be A. And 0, 0, 0, 1, 0. That can be B. 0, 0, 0, 1, 1 can be C. 0, 0, 1, 0, 0 can be D. Okay, so forth. And I get down to Z would be 26. What's 26? Well, I mean, I'm doing this in a certain order. I think you can see this. I'm starting off giving kind of priority to zeros. Okay, let me put a 1 there, and 1 0 and 1 1. Why am I doing that? Well, because that's binary. It's the binary numbering system. Well, let me just kind of pause and talk about binary numbers. Okay? How many of you know how to write numbers in Roman numerals? Oh, good. There. I know. I'm coming back to him. So he redeemed himself. He knew it was 2 to the b equals this. So that's all right. This way you can so tell us about Roman numerals. 7 Roman numerals. Yeah. What year were you born? 1991. How do you do 1991 in Roman numerals? You forget that. Okay. All right. It's M, no MCM, okay, MCM, uh, XCI. I thought you had Roman numerals again. How did I get that? Well, in these Roman numerals, you know, 1 is just like that, okay? V is 5. The 1 is a 1, right? V is a 5, and X is a 10. L is 50. C is 100, okay? M is 1,000. Yeah. Actually, there's a D. D is 500. Yeah. And then basically, you just pick these letters, it adds up to the right amount, okay? Except they have this little shortcut. The bigger the number is, it's supposed to be to the left, and the small part's supposed to be the right. But they cheat, okay? I mean, they could write this M, could write this M D D C C X C. But that's just so. If you put the C before the M, it's a subtraction, right? So this M here's 1,000. This second M is also 1,000, but since it's got a C in front of it, it's 900. Okay. And then this is 100, but the X in front of it makes 90. Okay. 1. Okay. Now, the Romans used that. What was wrong with that? By the way, you still use that. I mean, Rome and Greece was kind of our, cultural, the cultural forefathers of Western science. Why don't we still use the Roman system? Because it's a lousy, really bad system. What's wrong with it? Well, how would you multiply, say, 1991 by 7? Tough, right? Tough as the Romans. Romans, were not really good at multiplying. So the Roman numerals, is because people didn't really know how to do numbers well, at that point. Uh, the whole secret was this positional representation. And so we have, say, the number 1991. What we mean by that is 1, okay, plus 90 plus 900 plus 1,000. That's what we mean by that. We just don't write it out all in a lot of detail, right? And then so we add them together. I mean, this is just a short form of this right down here, right? And actually, another way of doing this is 1 plus 9 times 10 plus 9 times 100 plus 1 times 1,000. You see, those are powers of 10, right? So it's 1 plus 9 times 10 to the first power plus 9 times 10 to the second power plus 1 times 10 to the third power. So it's this positional notation, okay, is the secret, okay, to having a good number system, because then multiplication, addition and multiplication become fairly easy things to do. Actually, this 1 is times 10 to the 0th power. Anything to the 0th power is 1, okay, except 0. Okay, so here's a quiz for you. Whoever gets this answer first, I'm going to give one of these old emerged books to, okay? How would you represent, say, 2012, okay? And Roman numerals, okay? Get the answer, hold your hand up. If you got it right, I'll give you one of these books. Okay, what's the answer? MM. That's great. See? Okay, so um, the binary number system just uses twos instead of tens. Okay, and so it's B0. This is a binary bit. Okay, multiplied by 2 to the 0th power plus B1. That's a binary bit times 2 to the first power plus B2 times 2 squared plus B3 times 2 cubed plus blah, blah, blah. Okay? And these B's, B0, B1, B2, B3, are either, they're all, each one of them is either a 0 or a 1. Okay, so here's the second problem. Tell me how to represent the number 51 in binary. Get the answer all over your hand. That's the right answer. I use the, I only got 2 of these books. I can't get out anymore. And you're not, you can't do it. You can't win 2 books. Only 1 book max. Well, it seemed to be a little harder than I thought. 51. Well, let me do a few. Oh, you got it. Okay. What is it? One, I'm sorry. One. Little two. Uh-huh. To the base two. That's right, of course. But I hadn't talked about that. That's that little base two thing. I don't mean it's not decimal. This is a binary. Okay. The little two means think of all this as a binary. Okay. So it's going to be one. Let's start with this one over here. That gets multiplied by one. Okay. Plus this one right here gets multiplied by 2. This 0 gets multiplied by 4. This 0 here gets multiplied by 8. This 1 here gets multiplied by 16. This one here gets multiplied by 32. Okay? So 32 and 16 is 48. Okay? 0 plus 2 plus 1, 51. All right. So let's count in binary. Okay? 0, 1, 2. That's 2. Okay? Why is that 2? Because it's 1 times 2 to the first power plus 0 times 2 to the 0th power. Okay? Notice that in binary, 2 looks like 10. 3 is 1, 1. See? 2 plus 1 is 3. 4 is 1, 0, 0. Okay? 1 times 4, 0 times 2, 0 times 1 is 4. 5 is 101. 6 is 110. 7 is 111. 8 is 1000. Now, the powers of 2 always are just things with zeros next to them, okay? So, this is 2. Well, actually, this is 1. This is 2. This is 4. This is 8. This is 16. This is 32, right? Just like in the powers of 10, okay? You have 10, 100, okay, it's 10 squared, 1,000, 10,000, 100,000. So that's how we count in binary. Okay, so we've seen that there is a code called ASCII. I talked about ASCII last time. Let's see here. Okay. Johnny Harris? Aji? Aji. Ajan. 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 Coco. Okay. Uh, what does ASCII stand for? Oh, okay. You knew that. You learned it last time, didn't you? You remembered it all this time, huh? That's the satisfaction you get from being a teacher. American Standard Code for Information Interchange. And what it does is it's just a code in binary for storing characters, mainly like the characters on the keyboard. Keyboard of your digital device. Okay, so it has all of the 26 characters of the English alphabet in caps, all the 26 characters in small letters, all of the digits, 0 through 9, and then a whole bunch of special characters like parentheses and ampersands and at signs and pound signs and things like that. Okay. This ASCII code is stored in 8 bits. How many states would that be? 2 to the 8th power. How much is 2 to the 8th power? 256. Okay. So there's 256 states. Well, it seems a little bit like an overkill, doesn't it? We got 26 small letters, 26 big letters, that's 52. 10 digits is 62. It's a special character. 256 is way more than we need, right? Well, in fact, the ASCII code, when it was originally developed, was a 7-bit code. It actually was 7 bits, okay? And then they just store it as 8 bits because in computer a byte is 8 bits, okay? And so storing it in 7 out of 8 bits was kind of, you know, not quite right. So basically, the first bit in the ASCII code is always 0. It really only uses the bottom 7 bits. Okay? Now, how do we find out what the ASCII code is? Well, why don't we find everything? We Google it. we something else that we snap to it. Okay. ASCII table. ASCII everything to do with the ASCII table. ASCII definition. ASCII table character codes. ASCII Wikipedia. Oh, Wikipedia is the source of all knowledge now. Well, let's just go to the first one and see what it looks like. That's not what I expected. I think it's a. Oops. What happened? Yeek. Yeah, that's unusual. What happened there? Google it. Let's see. What? If I go to what? Oh, images. Let's see. Oh, good idea. Here's a good one. This looks good here. Here's the ASCII code. Okay. Now, it's a little hard maybe to understand this table here, as it will be other tables, because this table has rows and it has columns. These columns are 0, 1, 2, 3, 4, up to F. Okay, now anytime something goes from 0 up to F, a computer person says that's hexadecimal. I know other people don't necessarily say that's hexadecimal, but computer people say that's hexadecimal. Hexadecimal is binary shorthand. The bad thing about binary is it only have a 0 and a 1. And so if you have very many states, you get to looking 0, 0, 1, 0, 1, 0, 0, whole big long string of zeros and ones, and it's kind of hard to fathom. So in hexadecimal is just binary shorthand. We write 0 in hexadecimal, and what that means is 4 binary zeros. And we write a 1 in hexadecimal, and that's a binary 1. A 2 in hexadecimal, that's a binary 2. Down to a 9, okay, in hexadecimal, that's a binary 9. And we 10 is a B, B, okay, down through F. F is 15, okay. F is 1, 1, 1, 1, okay. So rather than write these things here, all these zeros and ones, we write a hexadecimal character. So In hexadecimal, 0A, what I mean by 0A is in binary, 4 zeros, and A is a 10. The 8 and 2 is 10, okay? So that's the A, that's the 0, that's the 8. So if we have 8 bits, rather than writing down 8 bits, we write down 2 hexadecimal digits, okay? So here's what this means. Coming down here, this is the first hexadecimal digit, and across here is the second hexadecimal digit, okay? So we mean if we want to store, say, a capital A right here, it's 4, 1, okay? It's hexadecimal 4, 1. Hexadecimal 4, 1. But in ASCII, the 4, you write it 0100, that's 4, and the 1 is 0001. So actually, these are the 8 bits, okay, for storing the capital letter A. So if you type the letter A in caps on your keyboard, what goes into the computer is this right here. That's, that's how A looks to a computer. Binary. I mean in ASCII. Well, for many years, the ASCII code was kind of the main thing. Nowadays, there's more of an emphasis on something called Unicode. And instead of coding things in ASCII, you'll sometimes find things coded into Unicode. What is Unicode? Well, Unicode is an attempt to have one code for all of the alphabets in the world. Just one code. Everything that anybody ever writes down in any country, in any language, okay, any dialect, okay, has a code for that character. Okay. Well, it's Unicode. It's a little bit complicated, I guess. Okay. Here's Unicode. Well, as you can see in Unicode, you can write the Armenian alphabet, the Coptic alphabet, the Cyrillic, the Georgian, the blah, blah, blah. Where's English in here? I don't see English anyplace. It's not there. The code that we use, the version of the Unicode that we use is called Latin 1. This is Latin, okay? All of the languages that use the Latin alphabet, okay? Unicode is 16 binary bits. Each character is 16 binary bits. So in Unicode, if you wanted a capital A here, it's 1004. I'll read that or not. 1004. So capital A in Unicode is 1004. It's 1004 in hexadecimal. So A in Unicode, that is the Latin part. Those that use Latin letters, okay, Roman letters. Okay. See, in English and Spanish and French and most of these Western countries all use Latin letters. They go back to Latin. Okay. And so it's 1004. Okay. Oh, I'm sorry, that's wrong. Here was it's 0041, sorry. Because in this particular case, the way they did this, these three go first, and this goes at the end. So 0000, 0010, 0020. So A here it would be 0041. It's the same as in yeah, the same as in ASCII. Okay, it just has two zeros in front of it. Well, it's kind of interesting. What all they have here anyway? Middle Eastern scripts, Ethiopian hieroglyphs. Hmm. Right. Oh, Egyptian hieroglyphs. Yeah. Oh, there's Egyptian hieroglyphs. Yes, you can't see that, but see, here's the Egyptian hieroglyphs. So if you go read some hieroglyphs, okay, or in Egypt, and you'll say, well, let's store all that information on a computer. That's how you do it, okay? You see this particular glyph here in Unicode. It's 13000. Whoa, 13000. That's each one of these is four. That's 4, 8, 12, 16. Whoa, 20. In Unicode, it's 16 bits, and there are some extensions, okay, to 3 bytes, okay, and even some to 4. But anyway, you can store Egyptian hieroglyphics. How about Chinese? Where's Chinese? That's got to be the acid test. Okay, it's Chinese first. Chinese. East Asia scripts. CJK Unified Ideographs. Han. What do you suppose that means? What do you suppose the Han means? 31 megabytes. Whoa. Han was the Han Dynasty, okay, in China. Okay. And so they came up with, whoa, look at that. Hmm. So this thing is 525 pages long. And so in Unicode, if you want this character here, it's 4E01. But why are there so many of these things here? The C means that's how they do it in China. J means that's how they do it in Japan. A K means that's how they do it in Korea. And V means that's how they do it in Vietnam. Notice in China, they'll do it three different ways. I mean, the Japanese always do it the same way, and Koreans and Vietnam, but China's a big country, and it's kind of hard to get everybody to do it exactly the same way, right? And so this character right here, I think, means strength, doesn't it? It means strength. Who's, who reads Chinese? Hmm? Nobody? You do Chinese? You know that strength. Well, at one time I worked with the Japanese. You know, in the computer business, you've been around long, you're naturally going to work with the Japanese. And so I learned a lot of this at one time, but I've forgotten it now. So anyway, this Unicode allows all these alphabets, and so basically computers nowadays have everything is about. So anyway, what I'm talking about today are data types. On a computer, when you store information inside a computer, you store that information in one of several different data types. Now, these data types, there are elementary data types, and then they're complex, I guess. Okay, and so at the elementary level, we have a character as we store characters. This is like every time you hit a key on the keyboard, that enters a character in the computer, and that would be stored as a character data type. And there are integers, and there are floating or real numbers, and so this character data type is what we store basically in ASCII or Unicode. Integers, that means whole numbers, both positive and negative, and zero. These are stored in binary. And real numbers are stored in a special data type for real numbers. Now, these aren't the only elementary data types, okay, but these are I guess, the most usual data types. Now, these can be combined, these elementary data types are combined into bigger, more complex data types. Okay? That is, we might store a picture, a regular picture, okay? You take it with a digital camera. You store that in a computer. Well, somehow you just take a bunch of characters and put them together, okay? And that forms a picture, okay? And these higher levels can be formed different ways. I mean, pictures on a computer, you can store a picture on a computer in probably 100 different ways. But the most often way that pictures are stored on the computer is called JPEG. Okay? And you can store sound and so forth. Okay? I'm out of time today. So what I'm going to do, let's go back to the textbook here, or to the slides. Okay. So today I talked about bits and bytes. Okay. I talked about ASCII. I talked about the binary number system. Okay. I've got a little bit more to say about ASCII and the binary number system and bits and bytes. Okay. And I'll finish that next time. Okay. But then go on. Okay. According to our agenda. Any questions? All right. Thank you very much.